Okay, so it's 12 o'clock, we'll go ahead and get started. I think the first thing I will talk about is the first midterm test. We're still a little ways out. That first test is the 21st of October. I checked the calendar just before I came, so we're not 3 weeks out, but still a little ways. So for that first test, the first reminder I would give you, if anybody receives any sort of special accommodations for testing environments, you should probably be contacting the Blundin Center today to get that arranged. They get more and more swamped every single year, and they do require a full 2 weeks notice before they can book you in for a test. So if you get those accommodations, you should talk to them as soon as possible. I can't provide any special accommodations in class. If you just forget to call them or whatever, then I'm sorry, you just have to write with everybody else. And that's for people who get accommodations. When you're getting ready for the midterm test, I would say your best bet is to review the lectures. You know, at the start of a course, I think about the things you should learn in this class. Those are the things I put in the lectures, and those are the things that will go on the test. So reviewing the notes is a good place to go. Every class has homework questions. You should be able to do those without looking at any of the answers. So you should be working on those homework questions regularly. The assignment system I did shake up a little bit this year, and the assignment system we have now is closer to midterm testing than Master in Physics ever was. So those assignments should be good preparation as well. Also the problem sessions, those are developed to help you with test preparation. Some people maybe found the problem session a little bit challenging, and that's kind of the point. You go into a low stakes assessment to get you ready for the higher stakes one. So those are all good things to study. It is my habit with smaller classes, like you all, to let students bring in a sheet of notes to the test, and I'm going to keep that up this year. So if you wish, you don't have to, you can bring in a sheet of notes to the test. A couple of restrictions. Don't get silly with sheet size. You can't bring in a sheet of Bristol board. So a sheet of paper, 8.5 by 11. Just the one side, please, so just one page. And here's the big one, and I'll be a stickler on this. It needs to be in your own handwriting, so you have to make this sheet. You can't just photocopy your friends, okay, so it just has to be yours. No restrictions on what you put on it. You can write whatever you want on that sheet of notes. So that's on you. I'm not going to inspect it for content and say, no, you can't look at this or you can't look at that. You may put whatever you wish on that sheet of notes. Okay, any questions? Yep.
You're going to have a formula sheet though, right?
Oh yes, I will still provide a formula sheet, and I'll post that when we get closer to the test. The cutoff date for the test will be a few lectures before the test. I'll let you know once we get closer. Yep.
Is it only one sheet, or is it the sheet on the back of it as well?
Just one page, one side.
Oh.
Yeah. Okay, I know not everybody lets you bring in a sheet, but I think it's okay. Not just my philosophy of teaching. Okay, so if there are no other questions, last day we finished off interference. Here's one last problem you can try. I will be posting that answer. Today we're going to get started on chapter 21. That assignment is open, so you're able to try that whenever you have time to get to it. So chapter 21 is all about electric charge, electric force, and electric field. It's really a very important concept and important topic. Sort of in the big picture, the universe has 4 forces. So there's gravity. Everybody knows about gravity. It's what makes stuff fall down and what makes the earth go around the sun. So gravity is an important force. There's the strong force. That's what keeps the nucleus together. There's the weak force. That one I don't understand very well. That's all about transforming quarks. That's beyond my pay scale. And then there's the electromagnetic force. So the electromagnetic force, and here's what I think is super interesting. If you think back to Physics 1020 or 1050, whichever class you did, and you drew free body diagrams, all those forces you put on a free body diagram, except for weight, all of those forces were really the electromagnetic force. Tension is electromagnetic, friction, normal forces, they're all electromagnetic forces when you get down to kind of the atomic level. So I think that's really kind of interesting. So electromagnetic forces, along with gravity, kind of govern our everyday life. So it's a big topic, and we're going to study it for a while. in the pre-COVID days, and I do miss those days so much, I would have brought in balloons for everybody and had people blow up balloons and kind of try and bring them together. I don't feel super great about having people breathe into balloons and have them pop, because heaven knows any one of us could be COVID positive and just not know it. So I did a demo at home and did a video. I'm sorry, this is the best I can do, but this is try this at home physics. If you have 2 balloons and a friend, you can do this. Okay, so there's the physics. When you rub the balloon on your head, there's a lot of stuff happens. Electric charge flows through the ground, into your feet, through your body, through your hands, and onto the balloon, out of your hair and onto the balloon. The balloon picks up electric charge. So I was doing it, that's my husband in the picture. He was doing it on his hair. We did it for roughly the same amount of time. So we had roughly the same charge on the balloon. So we both had the same kind of charge. We both had about the same amount of charge. And then when we tried to put it together, the balloons wouldn't touch. So this is something I expect everybody knows about. When you have 2 charged objects, if they're like charges, those like charges repel. So I'm thinking this is familiar from everybody's previous physics experiences. Something you may have thought about or not thought about, but electric force, like the gravitational force, is what we call a long-range force. It doesn't have to touch, it's action at a distance. So it pushes on each other without physically touching each other. So that's another part of the electric force. So here's a recap of things I think you probably already know, but let's go through them anyway. There are 2 kinds of charge, and charge is going to have the symbol of Q, either a lowercase q or an uppercase Q. Could go either way, kind of depends what I feel like at the moment. The units of charge are coulombs. Which has a symbol of a capital C. We often use microcoulombs. You're going to see that one a lot. That means times 10 to the minus 6 coulombs. You should definitely know that unit micro. If you asked me that on a test, I probably wouldn't tell you what micro stood for. I would expect you to remember. So microcoulombs, and sometimes we'll use nanocoulombs as well, where nano is 10 to the minus 9 coulombs. And we use that because charges are small. Okay, so we use micro and nano because they're really small. What do we have next? So we have our 2 kinds of charge, positive and negative. Protons have a positive charge. So charge on a proton you might call Q with a P. That's going to be positive. Charges on electrons are negative, and charges on neutrons is 0. So neutrons are neutral, protons are positive, and electrons are negative. We have a fundamental or a base unit of charge that has a symbol of a lowercase e and a magnitude of 1.6 times 10 to the minus 19 coulombs. This amount of charge is what's on a proton. So a proton is plus E. And this amount of charge is what's on a neutron, is on an electron, sorry, minus E. On a test, I would give you the value of E. Probably you're going to end up remembering it, maybe you won't. But you definitely have to know that protons are positive and electrons are negative. So that's definitely something I would not tell you on a test. Because protons, electrons, and neutrons make up everything, and because protons are plus E and electrons are negative E, a neat thing that happens is that charge is actually quantized. Every charge in the universe that you could possibly measure, you could possibly figure out, except for quarks, because quarks are weird, every other charge in the universe is a multiple of E, an integer multiple of E. So that's what we mean when we say charge is quantized. So if we wanted to find the total amount of charge on anything, we would take the number of electrons, multiply it by the charge on an electron, take the number of protons multiplied by the charge on an electron, and that would give us the net charge on any object. And that would be an integer multiple of E. Might be negative, might be positive, but it is going to be an integer. Another neat thing about charge is that the universe at large, charge is conserved. So you can move charge around, you can take it off your hair and you can put it on a balloon, but you can't create charge and you can't destroy charge. So that's what we mean when we say charge is conserved. So from the birth of the universe to the death of the universe, there will be exactly the same amount of charge. No change at all. Maybe moved around a bit, but the same size of charge. For a straightforward example, how many electrons would we have if something had a charge of -1 microcoulomb? So what would be the total number? So we would say our total charge is the number of electrons times the charge on one electron, because we're talking about electrons here. So our number of electrons would be Q total divided by minus E. -1 microcoulomb, that's where we remember a microcoulomb is 10 to the -6 coulombs, divided by -1.6 times 10 to the -19 coulombs, and we would end up with 6.25 times 10 to the 12. So lots and lots of electrons in a 1 microcoulomb charge. Okay, any questions? Historically, the Greeks around 600 BC, they're sort of credited with discovering charge. I guess maybe everybody knew about it though. You know, all the cultures would have rubbed things and saw that they attracted or repelled, but the Greeks are kind of associated with it historically. So then next, some of the material properties we observe are a result of how charges can move around inside the materials. So in general, protons are not free to move around. They have to stay put when they're in a material. Electrons may or may not be free to move around. If we have a substance called a conductor, they have the nature that charge can move freely through it. So if charge moves freely through it, then it's a conductor. Examples of conductors are metals. So a hunk of aluminum or a hunk of copper, you know, things you have in your wiring. If the charge doesn't move easily through it, then that's an insulator, so something like wood or plastic. And then we have special cases of semiconductors, and depending on the specific semiconductor and what we've done to it, maybe charge moves, maybe it doesn't move. So semiconductors are special. This is not a course about semiconductor. Physics does offer courses about that if you find it interesting. Probably engineering does as well. But this is not a class about semiconductors. So for an example of charge moving around, let's say that we have a plastic rod, and we take this plastic rod and we rub it on our hair so that we get it charged up. Then what we'll have is two metal spheres. So in one example and the other example. In one case, we're going to connect those spheres with a plastic rod, an insulator, and in one case, we'll connect it by a metal rod, a conductor. The behavior in those two examples would be a little bit different. In this example, when we bring that charged plastic rod close, from our balloon experiment, we know that like charge is repelled. So the electrons in this metal are going to be repelled by the electrons in that charged metal rod. They're going to move away from it, so the electrons will move away. They get here to the surface of the metal. They hit the plastic rod. They can't move through the plastic rod, so then they stay put, and we don't get anything on this metal sphere over here. So that's what will happen if they're connected by an insulator. In this example, the electrons in this metal sphere are repelled by these electrons, so they're going to get pushed away. Then they come to a metal rod. They're allowed to travel through there, so they will, because they're trying to get away from that plastic rod. Then they come to this sphere. They're also allowed to travel through that, so this sphere is going to end up more negative. So charges can move through metals, but not through insulators. We're going to talk more about the nature of this and how we apply it when we get into our next chapter about Gauss's law. So this sort of motion is going to be pretty important. Okay, so that's about the nature of materials. Next, we'll talk about the force, or we'll recap that force just a little bit. So things we know about the forces between electric charges. We know that if we have two neutral objects, they're not going to attract each other, so there's no electric interaction between those two at all. A charged object will in fact attract a neutral object. That's sort of interesting. I'm not going to go through it. You can read about that in your textbook. There's a page or two that explains that. If as a kid you took a balloon, you gave it a good rub on your head, you could stick it to the wall. Anybody do that before? You can make it stick for a little while, right? It wouldn't stick forever. That effect is called polarization, and your book kind of describes that nicely in a qualitative way. We know that objects with like charges repel. So two positives will repel two protons, two electrons, two whatevers, as long as they have the same kind of charge. If we have opposite charges, we know that they attract. That's what holds atoms together. So your nucleus is positive because it has the protons swinging around outside are the electrons, they're negative. That electric force of attraction is what makes the atoms stick together. And then the force between the charge objects, it depends on how much charge we have and how far apart they are. So things that are close will have a bigger force, and if there's more charge, there will be more force. The direction of the force depends on the signs of the charges. So there's some things that we know. So next, we'll talk about Coulomb's law. So Coulomb was a French physicist, late 1700s, so this is a long time ago. He studied charge and electric force, just like lots of people were doing at the time. 1800s was a big time for electricity and magnetism. Coulomb, in his experiments, he used a torsion balance, and he actually measured the size of the electric force, so he could measure how big it was. As a result of his work, he was able to write down an expression for the electric force, and that's what we call Coulomb's law. So Coulomb's law says if we have two positively charged particles or two negatives, then if they're a distance r apart, they will have a repulsive force between them with a magnitude of F, which is K times the magnitude of the first charge times the magnitude of the second charge divided by R squared. Okay, so some important things in this equation. This is the magnitude of force. It's the size. Magnitudes are always positive. That means we put in magnitudes of charges. So when you're using Coulomb's law, you always put in the plus values for the charges. Even if they're negative, you still put in the positive. So these are magnitudes. And then this one stumps people in high stress situations. R, physicists love to use R for distance. So R stands for distance. Sometimes you're in that time crunch, you see R, you think radius of a circle. Sound familiar with anybody? So you see R, you go, oh, I can divide that by 2 because radius is half a diameter. Don't do that. This doesn't stand for the radius of a circle. This stands for the distance between two charges. So you'll generally be given that distance or figure it out from the geometry. That's a force, so that's in newtons, of course. So this letter here, K, that's called Coulomb's constant. That has a value of 1 over 4 pi epsilon naught, okay, which brings us to epsilon naught. Epsilon naught is a constant. It's called the permittivity of free space. It basically means how electric fields can move through a vacuum. We'll circle back around to that stuff towards the end of the course. So for now, epsilon naught has a value of 8.85 times 10 to the minus 12 coulombs squared over newtons times meters squared. So when you use K, you can either do 1 over 4 pi epsilon naught, putting this value in your calculator, or you can have it pre-calculated as 8.99 times 10 to the 9 newtons times meters squared over coulombs squared. Okay, so we use that constant in calculating forces, electric forces. So that's the size of the forces. Let's just draw what they look like. So on my top picture, I have two charges. I'll call them Q1 and Q2. They're both positive, so they feel a repulsive force. So 2 is repelled by 1. 2 is gonna get pushed away, so we could call that the force of charge 1 on charge 2. Okay, I'm only gonna be picky about this notation for a few moments, saying 1 on 2. Later on, we'll simplify our notation a little bit, because I don't wanna write that stuff all day. Charge 1 is repelled by charge 2, so there's force of 2 on 1. Likewise, if our two charges are negative, Q1 and Q2, they still are repelled. F of 1 on 2, F of 2 on 1. So when we do Coulomb's law, and we're going to get around to doing some examples, we use the equation to get the magnitude of the force, and we use some sense to get the direction of the force. Remember that like repels and unlike attracts. Okay, that brings us to, if we have two oppositely charged particles, so down here we have a positive and a negative, Q1 and Q2. They have the same size force because it's KQ1, Q2 over R squared, but these are going to attract instead of repel. So this will have a force of 2 on 1, attractive, and this will have a force of 1 on 2, attractive. So far, so good. So the last thing we'll point out here is that in these forces, let's just look at the top one, the force of 1 on 2 is KQ1, Q2 over R squared. The force of 2 on 1 is KQ1, Q2 over R squared. They have exactly equal magnitudes, because you use this equation to calculate it, but they're opposite directions. Hopefully that makes you think about Newton's third law. So all of these force pairs we drew are action-reaction pairs. So they're all equal and opposite. And this idea will probably save you some time in problem solving, because lots of times you'll be asked to calculate the force on a certain charge and then on a different charge, and then you could use some of that action-reaction stuff to figure out the forces. Okay, are we still good? So let's see if we can get a sense of how big the electric force is. So let's think about a hydrogen atom, and let's find the electric force between the electron and the proton in the atom. So a hydrogen atom is just a proton, and an electron is going around it. The distance between the electron and the proton, that's a well-known number. It's 53 picometers, or 53 times 10 to the minus 12 meters. So we know lots about a hydrogen atom. So let's use Coulomb's law, and let's figure out the force between the electron and the proton in the hydrogen atom. So our electric force is F, I'm just going to put an E on it for electric, is K times the magnitude of the first charge times the magnitude of the second charge, divided by R squared. I'm going to call my first charge my proton, that's going to be Q1. And my second charge is going to be my electron, that's Q2. So I've got K times the charge, magnitude of charge on a proton, that's my fundamental charge E, times the magnitude of the charge on my electron, that's also my fundamental charge E, so E times E is going to give me E squared. And I have to divide that by R squared, where R is the distance between my electron and my proton. Okay, I've written down all these numbers in a table. I didn't want to get them mixed up when I was writing them down in class. So we'll put our numbers in. K is 8.99 times 10 to the 9 newtons meters squared over Coulomb squared, times E 1.60 times 10 to the minus 19 coulombs, that's squared, divided by R, which is 53 times 10 to the minus 12 meters squared. The number we get for the electric force of attraction between the two is 8.19 times 10 to the minus 8 newtons. That is a very small force. Good? Yep.
Is R just like a blatant given in this?
In this problem it is.
Okay, cool.
Yeah. Yep.
The values for like K and like G, they're only be given those if it was on a test?
Yeah. Although you're probably gonna find you remember it. You save yourself time if you remember all this stuff versus looking it up. Okay, so we're good with the electric force. To get a comparison, because we talked a little bit about gravitational force being the other force that governs our life, let's find the gravitational force between the electron and the proton, because we know objects with mass do experience a gravitational force of attraction. Just like the Earth and the Moon have a force of attraction, an electron and a proton will have an attraction. So our gravitational force is force due to gravity is G, capital G, Newton's constant, M1, M2 divided by R squared. M1 is going to be our proton, M2 is going to be our electron. Put our numbers in, G is 6.67 times 10 to the minus 11 newtons meters squared over kilograms squared, times the mass of a proton, 1.67 times 10 to the minus 27 kilograms, times the mass of an electron, 9.11 times 10 to the minus 31 kilograms, divided by that same R squared. What we get for our gravitational force of attraction is 3.6 times 10 to the minus 47 newtons. So that falls under the class of teeny tiny. So that's kind of interesting. We said that our electric force was small, so it was small, it's 1/100th of a micronewton, but our gravitational force is really small. If you wanted to compare it, you might calculate the ratio. Fe over Fg. You would get about 2 times 10 to the 39. So the electric force is 10 to the 39 times bigger than the gravitational force. I have to say, I don't have a method for understanding how much bigger that is. You know, my scale of understanding is my pen is about 1 centimeter, me is about 1.5 meters, to my house is about 6 kilometers, and across Canada is about 6,000 kilometers, right? That's about the scale that I can comprehend. So that would be a ratio of about 3 times 10 to the 8 from my pen to the size of Canada. I kind of get that, right? I don't get this, because that's just so much. We don't have a scale for understanding what that means. Beyond the fact that we can just say that the electric force is a lot bigger than the gravitational force in general. So let's get into drawing some forces. Okay, so let's take what we've just done and expand it a little bit. I've got 2 charges, Q1 and Q2. Q2 is twice as big as Q1. Let's draw the force, and we've already shown the force of 1 on 2. So they're like charges, they repel each other. Here's an arrow that shows the force of 1 on 2. So I'll give you a second. You draw the force that shows 2 on 1, and try and draw it to scale, as close as you can. I'm not going to come around and mark it, but just for yourself. If you're not taking notes, draw it mentally anyway. So the fast way to do this bit is just use Newton's third law. Force of 2 on 1 is a reaction force to 1 on 2. So those two forces are equal and opposite. So what you have on your paper should be a force that points to the left, and it should be the same length as this vector. So the magnitude of this force is K times Q1 times Q2 over R squared. The magnitude of this force is K times Q1 times Q2 over R squared. Okay, so they have equal magnitudes because you can find them both with Coulomb's law, same charges, same distance. Opposite directions because like charges repel. So this is a way to kind of evaluate those forces. And this will be the thought process, kind of when you're drawing force vectors, you can think about these relative sizes. Okay, next one, I'll give you a second to draw this one. I've got Q1 and Q2, same size as before, but now instead of being a distance R apart, they're a distance of R over 2 apart. So as best you can to scale, draw the force of 1 on 2, in keeping with the above problem. People have kind of had a go on it. So let's go for direction first. So the force on this one, is it to the right or to the left?
To the right.
Definitely to the right, because it's repelled, right? You've got two like charges, it's pushed to the right. Is it gonna be the same size as this one? Okay, I heard twice as big. Who agrees with twice as big? Anybody disagree with twice as big? Okay, other options? I got 4 times as big. Anybody thinking 4 times as big? Okay, any other options on the table? Okay, let's go through that process and let's see what we get. So this is a new system. I'm going to call my electric force F prime. It's going to be K times my first charge times my second charge, divided by the distance between those two things squared, R over 2 squared. So that's K times Q1 times Q2. Got to square both terms there. R squared over 4 equals 4, because I got a denominator of a denominator goes into the numerator. Q1, Q2 over R squared, 4 times as big. Okay, this one's tricky, right? Where it goes as R squared, it's not a simple linear dependence. Do you want to?
If there was no squared, it would have been double the length, but since it was the squared, it was
Yeah,
proportionally.
the squared stuff is important. So when we draw this one, you should have got it 4 times as long. So there's force of 1 on 2. When you draw force vectors on a test, I'll be looking for it sort of to scale, right? I'm not going to take it a ruler and measure anybody's, but definitely show smaller ones as smaller, bigger ones as bigger, and try and get the right directions. So that'll be something I'm looking for on a test. Okay, then we come to the last bit. Draw the net force on the charge at the lower left. So we want to find the net charge on Q3. So even if you didn't draw the first two, I'd like you to give this one a shot and try and draw the force on this one. Okay, and then we'll take a second and do that one too. And the reason I'm asking everybody to do it is because people lots of times get this one wrong, and I want to make sure you don't get it wrong on a test. Looks like not much drawing anymore. So I'm going to put this slide aside for a moment, and I'm going to come to this one that I call how not to draw the force. So often when I put this question on a test, and I see this problem even again in Physics 2055, somehow it just seems to take a little bit of time to really and truly sink in. So sometimes I will give the problem and I say draw the force on Q3, and sometimes the answer will come back with a picture that looks like this. So that's a force, and that's a force. Okay, that's a common answer I get back. If you drew that on your paper, you are not alone. You are not the only person who would have drawn that in this class. And then you'd come to me and you'd argue, but all these charges are repelled. Okay, fair point, those charges are repelled, but this is a force on 1, because I drew it on 1. That's a force on 2, that's a force on 4. I didn't ask for any of those forces, I asked for the forces on 3. So when you're asked to draw the forces, the net electric force on an object, you have to draw the force on the object. You're basically drawing a free body diagram. If you have a car in a street, you don't draw the forces on the truck that's parked on the next street, you draw it on the car. So when we say draw the forces on the charge, you gotta draw it on the charge, which means, and we'll do this on the next slide, so why don't we put a note there, must draw on Q3. So just like a free body diagram, the tails of a vector will start at Q3 and then you'll go in the appropriate direction. Let's go back to our last one. And let's draw them on that page. So Q3 is repelled by Q1. That's going to be a downward force. And I might call that one F1. So if you choose to keep writing F of 1 on 3, that's fine. I won't mark that wrong. I'm just going to simplify and say F1. My force of 2 on 3, I know it's going to be repulsive. Right off the bat, it's a little bit hard for me to get the exact magnitude. Okay, so I'm going to draw it repulsive, and I'm not going to give myself a hard time if I can't figure out the exact relative size. Then my force due to charge 4 is also repulsive. That's about the same size as F1. So there are my 3 constituent forces. I was asked for the net force, so I'm going to look at this and say I've got a force to the left, a force down, and a force that's partly left and partly down. So overall my net force is going to be left and down. So that's what that net force would look like. We're going to go through some examples of calculating these forces. In the meantime, I just wrote in a line about homework. I gave you the charges and the distance, find the forces, and I'll post that for solutions for you to check over. Okay, questions? All right, so now we'll get into an example of numbers. So our question is, find the net force on the charge at the top. I'm going to label my charges Q1, Q2, and Q3. Call my top one Q1. Call the lower left Q2, and the lower right Q3. I want to find the net force on the one at the top. This problem, I kind of wrote up a box as a process. Hopefully it's something you would kind of follow anyway, but sometimes it's good to write it down in words. This is not different from a problem you would have done in Physics 1020 or 1050. You'd be given a setup and you'd be asked to find the net force on an object. This is kind of the same deal. We've just got one extra step. So our first step is to draw the free body diagram. So we're going to draw the electric forces on Q1. So that's our first step, is to draw those forces. I'm going to draw them right on top of my diagram here. If you feel like you don't have enough room, you could go to a different diagram. So my force due to charge 2 is going to be repulsive. So there's my F2, pushing away. My charge due to F3 is going to be retractive, because those are opposite directions. I notice as I look at my numbers, Q2 and Q3 have the same size. So I think those forces are gonna be the same size, I'm gonna draw them the same length. So there's my F3. So there's your first step in figuring out any force problem, is to draw the forces. The next, and this step is new compared to 1020 or 1050. So in 1020 or 1050, you'd know those forces. You'd be given this one's 100 newtons, this one's 150 newtons, go from there. This time, we have to use Coulomb's law to figure out the magnitude. So that's our step 2, is to find the magnitude of the forces. Oh, last thing, I don't think I said this out loud yet. Because our gravitational force is so small, we generally just neglect it, we don't write it in. If you ever had to include a gravitational force in this kind of problem, it would be pretty clear in the problem. I would certainly specifically give you the mass, or I would tell you it's a heavy charged particle. So you would look for words like that, but mostly we just forget about gravitational forces because it's so tiny. Okay, now we want to find the magnitudes of the forces. So the magnitude of F2 is K times Q1 times Q2, magnitudes, divided by R squared. So R means our distance between our points, so between Q2 and Q1. So I'll label that R in my diagram. We see that's the same size as D, the length of that triangle. So this is equal to R. Okay, the magnitude of charge Q1 is little q. Magnitude of Q2 is big Q. R is equal to D. So I'll just rewrite that for us in terms of the symbols given in the problem. If you skip this step and just put your numbers straight in, that would be fine. So that's 8.99 times 10 to the 9 newtons meters squared over coulombs squared times 0.5 times 10 to the minus 6 coulombs times 1 times 10 to the minus 6 coulombs divided by 1 millimeter, got to put that in meters, so 1 times 10 to the minus 3 meters, that's got to be squared. What we get for our force is 4,495 newtons. Okay, so now I know the magnitude of F2. Everybody good? I also want to find the magnitude of F3, so that's the next step in my process. So that's K times the magnitude of Q1 times the magnitude of Q3 divided by R squared, which would be K times little q times big Q divided by D squared, which would also be 4,495 newtons. Okay, we can be real quick with that one because we get the same numbers as the previous part. Okay, so there's the second step in our process done. Now we go back to remembering physics 1020 or 1050. If we want to find the net force, we have to add up the forces. They're vectors, so we have to do a vector addition, which means we need the components of the forces. A pitfall here that people would do sometimes, you would just add up F2 and F3. So you'd add 4495 to 4495 and get an answer. You would get a size. Right after that, you know that can't be right because that's not an answer with a direction. Okay, so that wouldn't be a vector addition, so you can't do that. To add our vectors, we got to find the components. So we'll put a little star, and we'll say vector sum. An exclamation point. So let's draw our components on our diagram. So F2 is to the right and up. F2x will point to the right. F2y will point up. This angle is theta, which is the same as this angle, which is 60 degrees because it's an equilateral triangle. Yeah, I hope that's a little better. Then for F3, the x component is to the right. The y component is down. And that has the same angle theta with the symmetry of the problem. Okay, still good? So you got to show your components on the diagram as well. All right, now we'll use our trig to find our components. So F2x equals F2 times cosine 60 degrees 4495 newtons times cosine 60 degrees. That gives us 2,247.5 newtons. For the y component, F2y, it points out so it's positive, F2 times sine 60 degrees, 4495 newtons sine 60, gives us positive 3,892.8 newtons. So I used my sine and cosine to find the x and y components of F2. I'll do the same thing with F3. F3x is F3 times cosine 60. F3 had the same magnitude because those charges were the same size. So we get the same value for the x component. Positive x to the right and positive y to the up. So our x components are the same. That makes sense. They both point to the right, same magnitude of the vector, same angle. For the y component of F3, that y component points down, so that one's got to be negative. I've got minus F3 times sine 60 degrees, minus 4495 newtons times sine 60, equals minus 3892.8 newtons. So there are my x and y components. For my net force vector, I now have to add up the x's and add up the y's. So Fx equals F2x plus F3x. So I get 4,495 newtons for the x component of my resultant force. For the y component of my resultant force, I get, gotta add up the y's. 3892.8 newtons, subtract the same value, equals 0. So then to finish, you write your net force is 4,495 newtons in the x direction, or I hat.
Is this one of the few times that we get our calculators in degree mode?
Oh yeah, that's a good question about degrees versus radians mode. So when we do the oscillation stuff and the wave stuff, that's all radians mode. When we're back to kind of OG geometry, that's when we're degrees mode. If you're really stuck, you look for your angle. You see that's got a degree symbol? That tells you degrees mode. So this process right here, if you're working on an assignment and you're struggling with that kind of vector addition, I would recommend you come back to this and do it step by step. That process is going to get you to the right answer every single time. The next example is going to take more than 2 minutes, so let's quit there for today. Today is my day. I got to run to another class, so I can't stick around for questions, but I should be in most of the afternoon if you need to come